So the bond order in these is 1/2 the electrons in bonding orbitals minus the number of electrons in antibonding orbitals. So in this case with hydrogen, you have 2 electrons in bonding orbitals, none in antibonding orbitals, divide by 2, bond order 1, which is what we get from, Lewis structures. Any other bonding picture will give, has a consistent, if you can't say that, hydrogen only has 1 bond, then you have a method that's not, a theory that's not very useful. So the bond order, number of electrons in the bonding orbitals minus number of electrons in the bonding orbitals. What are bonding orbitals? Bonding orbitals are any orbitals that are lower in energy than the atomic orbitals that created them. Because if the combined orbitals are lower in energy, of course, that means that molecule will be favorable towards bonding. An antibonding orbital is an orbital that's higher in energy, any orbital that's higher in energy than the orbitals that were used to create it. Okay, so let's look at helium-2. Okay, so helium-2, we still only have 1s orbitals available. We still only have 2 1s orbitals available. That's what the electrons are in. And then when we come in, then we have 4 electrons to place. We place 4 electrons in the bonding orbital, but we have to put 4 electrons in the antibonding orbital. There's nowhere else for them to go. And therefore, the bond order is going to be 2, the number of electrons in the bonding orbital, minus the number of electrons in the antibonding orbital, divided by 2 equals 0. The bond order is 0. When we bring the atoms together, there's no net energy to be gained by sharing the electrons, because although some gain energy by going into the bonding orbital, the others are forced into the antibonding orbital, and the net energy gain is 0. And so He2 is not stable. That's what molecular orbital theory predicts. Okay, so let's draw some atomic orbitals and predict the stabilities. We'll explain the stabilities of helium-2 plus and H2 minus ions using molecular orbital theory. So let's draw some molecular orbitals, shall we? So we start out, this is easy, we just have 1s electrons involved. So we've got our atomic orbitals over here. So there's He, this is a 1s orbital, and here we go, molecular orbital, there's the molecular orbitals, there's the atomic orbitals, and we're looking at He2 plus. So how many electrons are in He2 plus? Well, that would be a helium atom and an He plus ion. That only has 1 electron, and that has 2 electrons. And so we get that, we fill it, we've got 2 orbitals. This is let's label them, sigma 1s, sigma star 1s. And so therefore we have 1 other electron. That electron goes into the antibonding orbital. And so the bond order, we predict, is 2 minus 1 divided by 2 equals 1/2. So it has about half a bond. It should be a little bit stable. And that's essentially what is seen, that the helium-2 plus ion is an ion you can create and has moderate stability. It's more stable than a helium molecule and a helium ion floating around. Together, they're more stable. Now, of course, they'll react with other molecules and form other things, because it's not that stable. It's stable with respect to the atom and the ion being separated, but not stable with respect to other combinations that occur. Other electrons that come, it'll suck those up, and you'll get a more stable helium atoms alone. But a helium atom and a helium ion are indeed more stable than if together than they are apart, and that is borne out by experiment. Okay, so what about the H minus ion? Well, actually, that's pretty much the same thing, right? We've got H2 minus, you will have 1s, right? Still, we only have 1s orbitals. So H2 minus, we've got, this is 1s orbitals here. We have H minus, which will have, actually, we'll put the H atom over here with 1 electron, and the H2, sorry, no, H is over there. These are atomic orbitals, so they can only have atoms or ions. H minus, oh, what do you know? We have 2s orbitals combined. We have, it's the same. We have a bond order of 2 minus 1 divided by 2 equals 1/2. 3 electrons, two of them in the sigma 1s orbital, one in the sigma star 1s orbital. And so we therefore have half bond order. And you could ask, well, what's the difference between these two? They got 3 electrons, but the helium ions have 2 protons in each of those. So those energy levels are all actually lower than the atomic orbitals, and the molecular orbitals are all lower than the hydrogen atomic orbitals and molecular orbitals, because helium has 2 protons rather than 1 proton. So the diagrams look the same, but the actual energy levels within each diagram are different because of the different nuclei. All right, so let's go a little further. Let's try lithium-2 and beryllium-2. So what is different about these? Well, we know that the 1s electrons are essentially inaccessible for bonding. When we do the molecular orbital diagrams, we only look at the valence atoms. But so what are the valence atoms here? They're going to be on each atom 2s. So let's do it here. We've got still our atomic orbital over here. And we have the 2s orbital is the only one. And the 2s orbital is the only atomic orbital on each atom, on both lithium atom here and lithium atom here that are accessible. And lithium has 1 2s electron, 1 2s electron. And so we have 2 symmetric orbitals. We're going to have a bonding orbital. This is now the sigma 2s, sigma star 2s. And so this has 2 electrons, and that's it. We've exhausted all the atoms that were, all the electrons that were in the initial 2 atoms. And so what we predict is lithium-2 is more stable than gaseous lithium atoms, which is correct. Lithium-2 in the gas state is more stable than lithium. Of course, lithium, we know you can form even more orbitals by putting a lot of lithium together, and that's the most stable. But this is still relatively stable with bond order 2 in bonding, 0 in antibonding, divided by 2, 1. So bond order 1. Let's look at beryllium. So beryllium, again, has only 2s valence electrons. So we have 2s here. We've got beryllium. We've got over here beryllium. And that's a 2s orbital as well. And they're symmetric orbitals, so we're going to get a sigma 2s and a sigma star 2s. And so we will start, beryllium has a full 2s subshell. And so we have 4 electrons, and we place all the electrons that were in the atomic orbital into the molecular orbitals. Remember, the molecular orbitals are replacing the atomic orbitals. And so now we have, it's entirely full. And so we would predict that Be2 is not stable because the bond order is 2 minus 2 divided by 0, 0. It's beryllium-2 is unstable. So that's a basic introduction to molecular orbital theory. And in the next segment, we'll start looking at how that applies to more complicated molecules when you start adding p orbitals in as well.